only going to use basically one equation. It's going to be that the pressure equals the pressure at the top of some liquid plus the density of the liquid times gravity times the depth. That's the hydrostatic equation. We used it over and over and over again. So what we're going to do today is talk about a bunch of different situations and devices, and maybe you'll see that all we're doing is applying this over and over again. Because in hydrostatics, that's the end of the story, pretty much. I wanted to look at one thing again. The very last thing we did last time, sort of rushed through it, and at the end, I think I didn't even do the numbers. We kept doing these situations, you may remember, like this, where we had some liquid like that, and it had atmosphere on the top, like that. And the problem was, and I realized the way I said it was a little misleading. I said, what if we raise this 10 centimeters? Okay? I'm sorry, well, we have to cut. Okay, if we raise this 10 centimeters, what happens? The liquid level stays the same. Right? The hydrostatic law, as I called it. It doesn't matter if you raise it. If these are both at atmosphere, they have to stay at the same level. So if you raise this would end up lower, it would just go up and this would stay here. That wasn't the problem. The problem was, what if we cap it? Right? So now, this has some pressure here. It might be atmospheric pressure, but it might change, right? Because gases are compressible. And I think what I said was, what if you raise this 10 centimeters? And then what's the pressure and what's everything going on? That wasn't quite the right thing to say. What I should have said was, raise so that the right fluid is, now I have room to draw it, is 10 centimeters above the left fluid. That's the more simple problem we're attempting to do here. So if your notes, if you have all this written down, just kind of scratch out the question and say that. Don't raise this whole thing 10 centimeters, raise whatever it takes to get one above the other like this. Well, you have to raise it to make it happen, like that. And of course the tube's actually flexible or something like this. Right, so this one ended up here, and this one is now here. And this difference is exactly 10 centimeters, 0.1 meters. And I think that's what I drew. But the good question I got that somebody asked was, well, if you just raise this 10, don't these things move a little bit? Do the two meniscuses, will they just sit exactly still and move? And we could actually look. It's in our demo. I spilled again. But there's a little bit of liquid left in this demo. It's still basically that situation, more or less. Right? So they go to the same level, and now we're going to cap this one that I spilled again. And as we move it up and down, before what we noted was that the two meniscuses don't stay at the same level now. It can go up. Oh, God. My cap. This is the wrong cap. Here's a cap. Here's my thumb. Okay. So they're at the same level, and now I can lift it and it goes up. Right? They don't stay at the same level. And we're about to calculate, that's because the pressure can change in here now. This isn't at atmospheric pressure, and this is. And that's why they can change. That's why they don't have to be at the same level. In fact, we could use the equations to figure out what is the pressure in here. Well, you would say now at this depth it's PATM, so it'd be up a little bit less. But it looks like it's not moving much, but it is actually moving. So if I let them go again and say this is exactly where atmosphere puts that one, if I raise this, it's hard to tell because everything moves, but it does move a little bit. Right? And the reason we don't deal with that, I had to think about it for a minute. The reason we don't do this sort of absolute, you move the container, how much does the fluid move, is because we would have to think about how much does this compress. The gas compresses or expands. Okay, so if you wanted the meniscus to change, or the level to change by 0.1 meter, the amount you move this would be a little bit different. And that's like PV equals nRT. We don't care about that. Okay? So if this confused you last time, if you're the person who asked or other people that were confused, what I meant to say was just the difference in the heights is 10 centimeters. And in that case, to solve it, all you do is apply this equation. Right? That's in the end, that's all it is. And we can solve it again real quick. If I can remember what the actual question was. Let's see. Covered container, raised 10 centimeters. Yeah, and then the question is, what is the pressure here? Right? That was the question. So let's go ahead and solve it again just for fun. So what do we know now? If we want to solve this problem, and we know that this is the only equation we ever use, how do we do it? Well, we treat this side, because this has the pressure we need. And we say, okay, and we say, what's the pressure somewhere at a depth where we know what the pressure is? How about here? Because of the law, we know that this side has to be atmospheric pressure right there, because that's where it touches the thing. We draw right across. It's a continuous single fluid. So we know that this must be at pre-atmosphere here. Right? And then we say, okay, let's write the law. The pressure of this fluid column at this depth is P atmosphere. So this is a case where the thing that we're usually solving for is the one that we know. And P naught at the top of the column is the one we're looking for. So that's what's a little bit different. Plus rho, the density of the fluid, gravity, and then the D. So it's just a case where we flipped around what we know and what we're looking for. Why do you spell gas with two S's? I was born in the UK, so that's why. Let's see. I spell a lot of things weird from that. Gray, McDonald's, all those things. Okay, so but we can actually solve this with numbers. We don't have to fight. We can solve this with numbers. Okay, so P atmosphere is 101,325 newtons per meter squared. Okay. P, the pressure above the thing, is what we're looking for. And these we actually all know. If it's water, it's water. The density of water is 1,000. Gravity is 9.8. And D was 0.1 meter. Right? So what is that? 900, it's, was it only 98 or is it 980? No, it's not 80. Right. So then the pressure is 101,325 minus 980. Newton per meter squared. I didn't calculate that out. So what that implies, though, is that this pressure drops as you raise it. So the pressure would go down. Okay, so I just want to make it clear that I meant to say the 10 centimeters up, not that I raised the thing exactly 10 centimeters. Right. And then you can feel it, too. You can feel the changes in pressure on your finger as you move this up and down. Ah, yes, like that. Yeah, so you can't feel it. Only I can feel it, so that's not a good demo. Okay. I usually put a balloon on it, but it was a rough Halloween. Let's just put it that way. Did you spell gas with... Good Lord, get over it. Yes. Jesus. Only when I make it plural. Oh, okay, it wasn't plural. Okay. No, you're correct. Even in the UK, it's only one S unless it's plural. Wait, is that the UK? I don't know. I spell a few things weird, but not that. Should we keep going? I don't know. Why don't you subtract the rho GD? Let's see. I was solving... Okay, so I totally wrote this wrong. What did I do? I was solving for P, and I brought this over here. Right? We're looking for this, so solve it that way. Okay. What we're going to do now is go through a few devices. Yes, that's correct. We're going to go through a few devices to measure pressure. All right, here we go. Let's do that. All right, cool. All right.